Okay, guys, in order to save some time, we don't have so much time left. I decided to do another exam review on video instead of in class, just so that we could do the last few lectures without spending too much time on other stuff. So let's look at the exam. Okay, well, I was kind of surprised again that some people still had, well, a lot of people still had trouble with this, and I'm finally beginning to understand why. Uh, um, with sketching the stress distribution across the cross section, and the reason for why you are still confused is that a lot of you did not really look at the detail. So it's not just the shape, but in which direction the arrows are pointing. Okay, so I'm going to skip the normal stress in bending, and I'm going to do the normal stress in axial loading. That one's the easiest. Okay, and so you can pick any direction you want, right? Because it's constant, but we have to present it somehow. And since we cannot show the vectors pointing into the surface, we knock them over horizontally, right? But the key thing is we need to do that. Just presenting in which direction the vectors go is not enough. We need to show the magnitudes. And that's the whole purpose of these little plots, these little sketches, to actually remember how the stress is distributed across the cross-section by magnitude. But the arrows show in which direction. Okay, so let's do it. So for axial loading, we said axial loading is always constant, right? So the normal stress in axial loading is always constant across the cross-section. So you draw that like this. So all the values for this point, for that point, for this point, for this point, all these points are going to be constant. And we draw the arrows. We can draw them in. That would mean it's some sort of compression. I assume that I am drawing these forces for these points, okay? Not for these points on the cross section, not like this or that, but along this line. And so this point has a stress that much, that point has a stress this much, and so on. That's what this diagram means, okay? So all these arrows are pointing away. That means it's in tension, right? So that's normal stress in axial loading. Let's do shear stress in torsion. So these two are the simplest case load cases, okay? We know that shear stress in torsion is the highest on the outside of the shaft and then 0 on the inside. So we know it's going to look like this. Now let's look at the arrows. Remember, we're plotting the stress for these points. So whenever you're in doubt, draw these little points and think how the stress will look in that point. So because we have a turning object, so this cross-section is turning, then the stresses will be pointing in here in one direction, here in the other direction, along this line. So that's how we draw shear stress. So let's say, look at this point, the shear stress is pointing that way. And it is in this plane that I'm drawing it. Unlike this normal that is actually vertical. It's going out of the page into your face. But we can't draw that. So we have to draw it some ways, okay? And so this is the shear here. So notice this line that goes away from this line, the line where the points are, and then the line that presents the ends of these vectors, which is basically the magnitude. How much? This much. This is 50. This is 35. This is 15, and this is 0. Okay. That the arrows are touching that line, whereas the lines at which we were looking at, the points from which where we're going to look for the stresses, there are no arrows at those points. Okay? Now, let's go back to this one. If this was a compressive stress, then our line would look like this. We would again have the same, the rectangular distribution, but now our stresses will be pointing in. So this is not, we cannot draw this as shear, because if this is turning, this way, then stress will be in that direction. So it's always going away from the point, not in the point. This is just for torsion, okay? All right, so that's good. So now we understood that it matters in where you draw these arrows, okay? Now let's look at the normal stress in bending, okay? So a lot of people remember that it has to look like this. But for the life of them, they couldn't figure out, and this has to be the same, right? Supposedly because I drew 0 here, that's where you started from, for the neutral axis. This is the neutral axis, but that's another neutral axis if the bending is in this plane. If it's bending like this, then the neutral axis is here. So because the neutral axis is right in the middle, these two should be the same, right? And so now all we have to decide, I know that this is going to be the magnitudes. So it gets bigger and bigger as we go close to the edge of the cross section. And now let's just decide on the arrows, okay? Remember what we said. When you bend a beam, I'm vastly exaggerating. So let's say we're bending it like this, okay? That's the beam. It's loaded in compression here, right? So I'm going to draw 2 arrows hitting each other. And it's drawing it's loaded in tension here, okay? So let me make those little guys up there. Whoops, that's a lot. A little separated. It's in compression here and in tension there, okay? So let's assume that we have this loading case, and then this is my cross section that I presented here. Draw me the arrows. Let's say that because it's circular, so this is the neutral axis going right through the middle. That means that these two by magnitude have to be the same, only in the opposite direction, okay? So this one is going to have arrows pointing to the line, into the cross section. Because this is a normal stress, remember guys, we just can't present it going vertical into our faces. We don't have a three-dimensional way of drawing on a computer. So we knock it over sideways, fall it down in this, collapse it onto this plane. Okay, so this one was going into the surface, right? So we draw into the surface, this line here. And on the bottom edge, it's in tension, so it's drawing away. So the arrows are here. So notice the difference between this case and that case. These arrows are pointing onto the line. These arrows are pointing onto the curve, onto the magnitudes, the inclined line. Here, all the arrows are pointing on the outside because they do represent physical vectors right there. Okay? These represent physical vectors that are up on the plane that is perpendicular to the page. So this triangle will be sticking out into our face. That triangle will be sticking away from us, behind your screen. Okay? So that is the difference. And I see that nobody got it. I don't think, I've just quickly glanced through the exams. I don't think anybody got it. You can also plot this. It will be perfectly valid. You can also plot it like this. You can also plot it like that. But again, you have to stop and remember where your arrows are, okay? So this arrow will be this way for the same case, okay? But for this case, the arrows will again be going this way. So do you understand? So that's the difference, okay? It just depends where you want to collapse this guy. This triangle is behind the page. This triangle is above the page. So how are you going to draw this in 2 dimensions? Whichever way you choose, the arrows have to be on the right side. Okay? All right. So that's the difference between this and that, even though they look the same. And now I want to say that this shear stress in bending, when I was making up exam, I totally forgot that I said that we're just going to stop at the flexure formula. This is actually after the flexure formula. So although you should know how it is because I just taught it, I'm not going to take any credit off for the people who didn't do it, and those who did, they'll get extra credit. Actually, everybody will pretty much get extra credit because I'm not going to change this number of points here. But the person, I think I can see one person at least did it, so they're going to get an extra 2 points just to make them up for the other stuff that they, if they messed up. So shear stress in bending is, we said, is 0 at the ends, and it's maximum in the middle, and it looks like this. Oops. I suppose I should learn how to draw with this pen. That's it. Okay. So it's some sort of curve, but it's basically it's parabolic, and it's equal to it's always 0 there and maximum in the middle at the neutral axis. Okay. So that's this problem. Unfortunately, you didn't use the opportunity to get extra credit here, like to get easy points. This is conceptual, and you need to learn this, okay? It needs to be learned. Okay, so here you just have to sketch, and I'm going to emphasize that. Use maybe a green pen. Sketch. That means use the graphical method for solving the beam. And so what do we know about a single force? And I purposely put it somewhere slightly closer to this end than to that end. It is going to deform the beam like this, right? Where is it going to push more? Clearly here. And if you do the moments equation, you will see that this force is going to be bigger than that force. This is a little smaller, that's a little bigger. Okay, so that means that my diagram is, when I draw them, is going to look like this. A little bit up, then horizontal all the way up to the force. Then it goes down by the magnitude of this force here, which we can say whatever we want it is, we don't know, and comes down here. And this guy is bigger than that guy. Okay, and so that's it. The arrows need to be here. This is your X, and that's the end of it. Okay. Now the moment, there will be no arrows in the moment, and we know there are no moments anywhere here, okay? So we know that it has to start at both supports, it has to be 0. And right here at this force has to be maximum. How do we know? Well, let's just look at this line here. So the value, this value is positive, and it doesn't change from one to another. It's constant, right? So for that's, if the shear is like that, the moment will be, the slope for the moment will be positive and constant, which means that we just have a big inclined line, straight line with a slope, okay? And then at this point here, because there's a jump in the shear, there will be a sudden change in the curvature, in the slope, right? So it will not be continuous, it will not be gradual, it will be sudden. And because this is constant in the shear, the moment will also be just a slope. And it has to come down to 0, but because there are no other moments. And that's our moment diagram. And everybody should be able to do this in sleep, because these are key things. Like these basic beams that you saw in the chapter, you need to know how to do each one without thinking. So I shouldn't even have to explain this, okay? When we have a continuous load, again, we will have, this one is completely symmetric. So we know whenever you have a symmetric load, whichever kinds of loads you have, you know that the two reactions, if you have a simply supported beam, will be the same. And that means that this shear diagram is even simpler, even though it looks like it maybe is not, because it's not a straight line. So this is this force. And here you'll have to have the same going up. And then you just have to draw a straight line, and this is right in the middle, okay? So this is your shear diagram. And then, and a lot of people, despite of me saying that you have to mark it, didn't mark it. So if I know what you're trying to do, but I want to see that you're consistent. I want to teach you how to represent your results properly. Okay, so please do what I'm asking you. Then the moments diagram, okay, we see what? There are no moments at either of the supports. So I know the moment has to go to this point. When you have a slope on the shear and it goes through 0, for that location, you will have a maximum or a minimum. And so let's just decide, is it going to be maximum or minimum in the moment diagram? So let's just decide, is it going to be a maximum or a minimum? What's happening with these two lines? Remember, you look at two neighboring values for shear, and you can see that the slope here is what? I mean that the shear um, uh, magnitude is positive decreasing, so it's bigger here than there. So the slope here will be positive decreasing, okay? If the value of shear is positive decreasing, the slope on the moment will be positive decreasing. So what is a positive slope? It's in this direction. Decreasing, this is steep, this one is less steep, so this is very steep, this is less steep, this is even less steep. So it's going to be dropping, okay? So that means it's going to be going up and then down. And so this should be perfectly symmetric. And because we know that the moment has to be really that the derivative of the moment is the slope, so or that the moment is the integral of the slope. The slope is of the first power of location, so it's like a linear function of x. So that's to the power x to the power of 1. So that means this one will be quadratic. So I asked you to write this, and you didn't. Those could figure out what it was. But this here is the maximum. At the maximum, there is no sharp, like here, there is no sharp change in slope. It's gradual. And so this is quadratic. It's a parabola, right? And that's our values. Okay? So that was easy. Next problem. Confused some, confused I think a lot, and everybody sort of knew, but they couldn't figure out. You guys have to get comfortable using general symbols, not punching numbers into the calculator immediately, okay? So the reason why I'm insisting on this is because the moment you start punching numbers into the calculator, you're removing yourself from thinking about the problem. You're going into an automatic mode, okay, like autopilot. I'm noticing that this is the biggest problem of all of you in the class, with maybe exception of one, that instead of thinking about the problem and sort of just thinking it out in your head, where is it going? You immediately start writing things down. I mean, I'm amazed. I was observing several of you as much as I could when you start solving a new problem. And it's a fascinating experience to see this, that you have not even finished reading. I cannot read it that fast. You immediately start writing. How is this possible? Okay, so you're really setting yourself up for problems. So what do you have here? You have all the dimensions, all the properties, and you're given a torque T, but you're told that you don't really know what it is. You only know where it is and in which direction it is. And so you want to basically choose this torque. How are you allowed to load this assembly to satisfy the absolute maximum shear stress? Notice I said absolute maximum. That means it doesn't matter in which part of the beam. I even spelled it out to you that it doesn't matter in which part of the cross section, but it does matter. Something else matters. Okay. Shear stress in the shaft is Tmax. Basically, I'm telling you that wherever on this entire shaft you have the maximum shear stress, it will be equal to this number. When you're given that the shear stress in the shaft is Tmax, that means it's a given information, 35 something, okay? All right. And then I even wrote in parentheses, and it wasn't enough, okay? That everything is given except T, which you must express in terms of all others, including Tmax, okay? And a few of you, I needed to tell you, to remind you to read this in order to get this. So I don't get you guys, okay? So let me move the text out so that I can use some of the white space here. I don't have that much space to write on this. I wish it could just, the whole text could slide with it, but it doesn't. Okay. All right, so let's start writing. So what do we have here? The very first thing I want to do is, as I always keep warning you, and I have not seen many people do that. I have seen couple actually sketch it. Okay, so I'm just going to make it really thin. It doesn't matter how it looks, but as long as it's clear what is what. And now I've removed the walls. It's a statically indeterminate problem, right? We have two walls. We can't, so we have two reactions, and we only have one equation for the torque. So how do we calculate the second one? And that's where we need to use our method, okay? So first you get rid of the walls. For torsion, you get rid of both walls. In axial, we just got rid of one wall, and then we did some complicated stuff. Here, it's super easy, okay? So this torque, because this torque at C is in that direction, the torque at A, I'll call it TA, is in the opposite, and then the same goes for the torque at D. Okay, and so I have these distances too. And now the key thing is to recognize, just like in the previous problem with the forces, use your common sense. The torques are external loads. They only depend, the reactions depend only on distances. They do not, it doesn't matter how thick the beam is, the shaft is, okay? And so, because you're calculating the amount of torque, okay? And so this torque clearly has to be the sum of these two. But which one will be bigger? It will depend on the location of the torque T. So the torque T is closer to torque D. So what do you think, which one will be bigger? Okay, so everybody can figure that one out on their own, okay? The bigger one would be the TD, okay? And we'll see if it comes out. I'm sorry, the TA. So let me not guess. Okay, let's just write the equations so that we don't get confused. So sum of torques is equal to 0. Okay, and from that we get and I'm going to choose. I don't have to write anything else. You can see that TA plus TD is equal to T. Okay, and we see that that's our first equation, and I'm going to highlight it like this. Please do this on the final, because I keep telling you, you just keep writing things on top of each other. You lose track of what you have, what you need to use, what you've already used. So highlight your key equation. This is your key equation. Next equation, compatibility. Okay, and that one says that the angle right here at C, the angle of twist, what's the angle of twist at A? 0, because it's fixed to the wall. The same thing at D, 0. But there is an angle of twist here, right, that will depend on this torque. So basically what you're trying to say is that the total angle of twist of C with respect to A has to be equal to the total angle of twist at C with respect to D. Right? That's a logic. It's not even mechanics. It's not something you needed to learn. It's common sense. So we're just going to write it as C with respect to A is equal to phi of C with respect to D. And so just let's write these two. So what is the phi of C with respect to A? Here I'm going to draw a diagram. And again, actually, what I wanted to say, I just realized I said it wrong, but I'm not going to refer to it. I guessed the TA and TD, but I don't have to. I can draw a random diagram because you will have to put in some values. So I'm going to draw a random diagram. These are no vectors, but I'm just going to draw a double arrow to indicate the direction so we don't forget where we are. And then this one goes up somewhere. And I'm going to draw them to look like they're the same, but they're not. So double arrow. And then TD comes down to 0. Okay. And why am I doing this? Well, you will see, because for compatibility, we need to remember where we are. And I'm going to write this is TA, this whole thing is T, and this thing here is TD. And I'm going to use my eraser to tidy this up a bit. Whoops, not so much. Why is it not doing it? Huh, okay. Sometimes it does it gently, sometimes it doesn't. Okay. All right, so that's my diagram. Oh, so now let's look what we had here. I'm going to use a red pen. So for compatibility, how do we write this? We know that the equation for phi is equal to, just a generic equation, is TL over the T internal torque at that section times the length of the section, and then divided by J of that section and times G of that section. All right. And so let's quickly write what the J of this section is and what the J of that section is. The J of this section is equal to pi over 2 and then R to the 4th power. And R is 2D over 2. It's the half of the diameter. So it's just D to the 4th power. J of this section is equal to also pi over 2. But now we got a little more work to do. We have D over 2 and the whole thing square. You know how many people I saw, they just write D to the whole thing to the 4th power, D to the 4th, and they don't raise the half to the 4th. You're in college. You should never be making mistakes like this, okay? It's just not acceptable, okay? Pi over 2, and that's 2 times 2 is 4, times 4 is 16, times 3 is 32. So it's pi over 32 D to the 4th, okay? And everything else we have. So let's just write it up. So for this, from C to A, that's this force here. How much is that amount? It's TA, okay? And so this equation will then read TA times the length is 2L divided by J, which is this J. It's a pi over 2 D to the 4th, and times G, which in this case is G half. Okay, and that's equal to phi C with respect to D. So it's for this section. What is the torque there? It's TD. So I'm going to write TD times the length is L. So I'm going to write L. The J is this guy here, which is pi over 32 D to the 4th, and then times, and the G is just G. Okay, some things are easier, some things are harder. And when you sort this out from all that, you get a very simple equation that TA is equal to 4TD. So we see TA is bigger than TD. So this was much bigger, like this maybe, and this guy was much smaller, like this maybe. And I'm purposely doing that because now I see that that's my maximum value. That's my maximum torque along the entire span. And this is tiny, okay, compared to that. And so now, because I have this, first I'm going to I'm going to get rid of the TD. I have this equation and that equation. And so from these two equations, I can express both TA and TD in terms of T. So some of you had decided to call this not T as I wrote here and insisted you not change anything about it. You just added a C to it. It's not acceptable. The TC would mean an unknown reaction at C. And you don't have a reaction at C. So do not use nomenclature that you're not supposed to use. So from these two equations, we get that TA is equal to 4/5 of T, and TD is equal to 1/5 of T. These are our reactions in terms of T. And the only thing that remains to do, and now I'm going to change pen to blue, we get this. Now we are putting in that tau maximum, okay? So we're told that the tau maximum, the absolute maximum shear stress for the entire beam shaft is tau max. So what does it mean? We need to write this tau max in terms of, everybody knows the formula, which goes something like this. I'll write it here. Tau is equal to T C, little c, over J, okay? And so now, in order to use this formula, we need to make sure that if we, for whichever section this internal torque T is, then these two also correspond to that section. But if you have tau max, then you have to say that corresponds to the maximum T. So that's T max times C for that section over J for that section. And now let's see which of these two T's, where is our maximum? This one or that one? Well, it's this one. And what is it? It's a TA. So T max is our TA, which is 4/5. Okay, I'll write it somewhere else, not here. So that's our T max. And because that's at the section AC, at this fat section, the bronze, then I'm going to just use everything for that section. So now we have tau max, and that's why I'm not writing in line, I'm just writing another tau max, is equal to, and now I'm substituting. T max is our TA, which is 4/5 of T. Times the C. What's the C? From the middle to the furthermost point, which is D, right? It's a half of D. So that's D over J. It's the J for this cross section, which is right there, pi over 2 D to the 4th. And then D to the 4th and D cancel. This becomes a 3. And finally, we have that that's equal to the 4 goes up, so that's 8/5 of T over D to the 3rd. And we need to find T. So now you remember that everything, what's given? A D is given. A tau max is given. So everything is given, you have to find T. This is the guy, okay? So T that we're looking for is equal to 5/8 tau max over D to the 3rd. And so now this is one way that you might be doing a design in the future. You already have a part and it's already in place and you know the material. So you know the properties, you know what's its tau max and you know its diameter. And you want to find out what kind of torque are you allowed to use? What's the maximum torque you're allowed to load it with so that it doesn't get damaged? Isn't that logical? That's the typical design problem you might be solving one day. Okay? Now, next problem. Next problem is just the shear forces and moments in bending. And what you were asked to do here, I will have to underline it. And again, I'm disappointed because, again, people just don't read the question. They don't read what you're asked to do and they don't give it to me. Okay? So shear and moment as functions of position x. Functions. What does that mean? F of x. That's a function of x. That means whatever the function's name is, you put it instead of this f, and then you attach parentheses with x inside. That means a function of x. Okay. So what do we need to solve here? I'm going to raise this and send the beam a little higher so that I can do my calculations. Okay. And at some point, I'm actually going to move it up a little, maybe make it smaller, like that. And then hopefully there'll be room down when I'm doing the moments. I don't know. Let's do it like this. No, I'll have to erase and do the moments, move it up for the moments. Okay, use another page or something. Okay, so let's look at the shear moment diagrams. Yeah, maybe I can do that, and I'll be spilling out to the side. How about that? Okay, so what do we have here? First, you have to do the free body diagram for the beam to find out the supports. So let's quickly do that. I can see from the loads that both the forces will be going up, will be pointing up, and this is AY, and this is BY. And I see, and then I draw these two, and this is a 10, and must not forget the moment 15. And now this is a complete free body diagram. So now we can start solving it, okay? I'm going to write here to save some space. So sum of y's is equal to 0, okay? And so that means that AY minus 10, I'm just going from left to right, minus 10 and plus BY is 0. And from that we see that AY plus BY is equal to 20. So that's our first equation we're going to use. Then sum of moments around, let's say, the point A. And I'm going to choose this as a plus. And so what do I have? That's equal to 0. So I'm writing 15. Well, why did I start from 15? Let's not start from 15. Let's start from AY. So the point A, this is point A, and this is point B. So moments around A, AY doesn't have a moment, 10 does, so it's going to be plus 10 times 2, this bit is 2, then plus 10 times 4, because for this force the distance is 4, then for BY it's minus BY times 6, and then plus 15. And that's equal to 0. Okay? And from that, we got another equation that BY is equal to 12.5, and this is in kilonewtons. And then when I plug that in up there, I get that AY is equal to 7.5 kilonewtons. Okay, so just for these purposes, I'm going to write here 7.5, and here I'm going to write 12.5, because I don't have so much space. Okay. And so now how do we draw? So basically now we divide into sections. We have 3 sections, and then we write our x. Even the people who did it right, who drew correct diagrams, had a serious trouble figuring out where they're calculating, and they kept switching where they're calculating their x from. Even though I forced you, I drew this x-axis here. It starts here every time, regardless of which section you're at. And I showed and emphasized that in class, nothing. It's like incredible. I do not understand why you don't want to pay attention. Why do you not want to accept it? But you didn't. So the first section, this is your x. The second section, this is your x. And the third section, that is your x. Okay? So this is x, and this is x. However, your x's go from what to what? I'm going to write the forces here and then the moments down there. So the x's go, for the first one, go from 0 to 2. So you have to write that down. You don't call this a section 1. The mathematical way to do the same thing, which is what I'm asking you to do, because that's what I've shown you in class, is that x goes from 0 to 2. And for that, what do we have? We have that v of x, that means a shear as a function of x for this is just equal to ay. That is 7.5. 7.5. It's constant, okay? Then for 2, the section 2, x goes between 2 and 4. Again, I'm not writing equal here, only goes up to 4. So again, x starts from here. And now we're counting ay minus 10, okay? So that's going to be our v of x is equal to 7.5 minus 10. And the value is 2.5, but it's negative 2.5. And lastly, we have the section from 4, and this time I can write both because we go all the way to the end, is v of x is equal to, again, 7.5 minus 10 minus 10. And that comes to be minus 12.5. And that's exactly equal to this by. So we are in good shape. Okay, so I'm going to leave these x's, and then I'm going to scooch this diagram a little, make it look a little slimmer than what I wanted. Let's do it like this. So it goes up. First value, just from 0 to 2, is 7.5. So that only 7.5 for this section. So that's 7.5. And I draw an arrow. And then I have minus 10 down, and we got to make sure. So when we look at this, this is minus 2.5 from 2 till 4. So from 2 till 4 is minus 2.5. It goes here. Maybe I drew it a little bit bigger, but this amount here should be 10. 2.5 and 7.5, it is 10, okay? So this is the graph. This is minus 2.5. And here is also minus 2.5. And then we go to section 4 to 6. The value is minus 0.12. So it goes even further down. And we know that this is minus 12.5. Minus 12.5. And so sure enough, this is minus 12.5. So this is our shear diagram, okay? Where this point here is also minus 2.5. But this amount here is 10. Okay? So this is our shear diagram. And now let's get practical and let's start writing the harder one. So again, the moments, right? From 0 till 2. That's the first section. Our moments look like this. And this is where you have to understand, this is why the x has to start always from 0, from this side. X doesn't start at the beginning of the section. You have to accept that, okay? If you say that x starts from the beginning of the section, you can still do it, but then you have to stick to it. You cannot be changing your mind halfway depending on what it suits you better and leaves you with less coefficients, okay? And so some of you have done that. The equations are completely wrong. But because now you learn how to do the graphical diagram, the diagram is correct because you drew the diagram without substituting the values into your function of x, okay? If you substituted, you would have seen that it's wrong. So let's start. So the first we're looking here, for this section here, the moment for that point in the section, that means you're looking for the moments around that point, is ay, it's positive, right? So it's ay times x. This is 7.5 times x. And that's all there is. And so we'll see how much that is in a 0, how much that is in a 2. Then we have the second section is from 2 to 4. And that's a little more complicated. Okay, from 2 to 4, we get this. We get ay, so now we're looking for this section, this point in the cross section. The moment of force ay for that point is ay times this x, right? And that's 7.5 x again. But now at this here, for that point, we also have this force. So it's pointing in the opposite direction. So it's going to be negative the force is 10, times what? Times this distance here. Okay. That distance there. And what is that distance? The purple distance is equal to this blue x, the long thing, minus this amount, which is 2. So that's x minus 2. And when you do the math, you get that the moment with respect to x as a function of x there is minus 2.5 x plus 20. Finally, we have from 4 to 6, and that's the hardest one. There's more work there than in the others. What do we have? M of x is equal to, again, this is the x here, this is the cross section we're looking for. And so now let's do the calculation for ay. The moment around that point is ay times the x. Again, so it's 7.5x. This force here now has a moment. This force here has a moment around this point of 10 times this distance. How much is that distance? It's going to be x minus this bit, which is 2. So it's again minus 10 x minus 2. So notice, if you keep the x right where it is, always at the same time, as the same point, you will be copying these functions. Look at the first function. The second section has the same plus something else. The third section has the first two the same plus the third term. Okay? Now the third term is going to be different. And so now we have to account for this force here. And that force here has the moment of 10 times this amount. Okay? Which is what? It's this x minus that amount, which is 4. So it's minus 10 times x minus 4. Okay? And that's equal to, when you add it all up together, you get minus 12.5 x plus 60. And so now the key point that you need to understand here is that these three functions of x are only valid each in its own range, in its own region. So this function is valid only here, this function is valid only between these two, and that function is valid only here. Okay? That means that this function, we calculate the values for the beginning and the end of that region by plugging in this and that. So for x equals 0, you get 0, which is logical. There are no moments there, so it should be 0. When x is equal to 2, this is 15. So this needs to go somewhere here into 15, okay? And because this was straight and this is a linear function, two reasons that we have to confirm that this is a straight line. So next, now we plug in 2 into here. 2 times minus 2.5 is 5. So this amount plus 20 is 15. Sure enough, there is no jump. At this point, that region is also, the function is also, the value is 15. Which is true because there are no moment jumps. There is a force jump, but no moment jump. And then we plug in the 4. 4 times minus 2.5 is minus 10, plus 20 is plus 10. So then this here, the value here should be plus 10. It's about up to here, approximately. And again, it's a straight line because this one is a constant. So this is a slope, okay? And this is 10. And then the last bit, now we're looking at this last section. We substitute 4 into this, and minus 12.5 times 4, and then that's 50, plus 60, minus 50, plus 60 is plus 10. Sure enough, we got the 10 again, so that's correct. And then 6 times all this, plus 60, oh no, 6 times minus 12.5 is 6 times 12 is, let me see, 6 times 12 is 72. 0.5 times 6 is 3, so 75 minus 75 plus 60 is minus 15. And that's this much here, so it should be around here, minus 15. And when you look at that, it's a straight line that comes down to minus 15. And sure enough, it doesn't end at 0, because here we do, that's the only place where you want to, maybe if you really need to put arrows for yourself, I would put 2 arrows for the moment, because we do have this moment of 15 right there. And so this is our moment diagram. Now, some of you got diagram, but the equations are completely wrong because you did not use the equations to get the diagram. So you didn't notice. Okay, but this is how you solve this problem. Okay, when you're substituting these two values, the value of 4 in this equation and the value of 4 in that equation, they have to come out the same unless there was a jump of a moment somewhere, and it wasn't. Okay, so that's how it works. Okay, here in this second problem, number 4, I wanted to just use. I wanted to work with your intuition, to reward you for your intuition, as long as you show me that you know how to manipulate the mechanics that you learned in this class. And you know, some people had trouble with it. Okay, so let's see. Even though I've talked about this exact thing in class and everybody participated, so you really sometimes you beat me. Okay, so you have a beam that is B by 2B, and it's exposed to some bending moment M. And so what orientation of the cross-section will you choose? This is a horizontal and that's a vertical, in order to maximize stiffness. I didn't tell you to calculate anything, just to maximize stiffness. And so in order to make sure, for me, to make sure that you are writing something down that's usable, I actually broke it down in questions, even though I should have just left it open, and then I know what would have happened. I would have gotten essays from you instead of math. So I kind of had to force you a little. But let's see. So what is the key property of the cross-section in beam bending? What is the key property of cross-section? The key property of cross-section could be the area. Unfortunately, in beam bending, area doesn't play a role. What plays a role, the key property, what plays a role is moment of inertia of the cross-section with respect to neutral axis. Now, I got this first from some people, but nobody wrote with respect to neutral axis, because moment of inertia is something that is relative to an axis. So it's never just moment of inertia, okay? It always refers to something. And so this needs to be indicated. It's with respect to neutral axis. So when we look at the horizontal and the vertical one, the neutral axis, I'm going to highlight them. This is the neutral axis, and that's the neutral axis, okay? And this is the neutral axis. This neutral axis, the material is distributed along it, and here the most of the material is distributed perpendicular to it. And so all of you, some of you intuitively, some of you because you're sort of really fixated on equations, you realize that it has to do with how far the material is from neutral axis. Yes, but now let's see how and what. Let's first answer this question, and when we come to this question, we'll talk about it. What are its values for these two cases? I'm going to call this case horizontal, and I'm going to call this case vertical. Okay? Okay, so let's write the I for the horizontal. So, or let's start with vertical. I vertical is equal to what? Is equal to the width to the first power times the height to the fourth power. The height is 2b. It's not the distance from neutral axis, it's the height, the total height. So it's equal to 2b to the third over 12. And actually, come to think of it, um, do I want to use the, let me think about it. Um, yeah, I'll continue with this. So the height for this, for the vertical one, is 2b. So that's 2b to the third, the whole thing, both the 2 and the b are on the third. And when you sort this out, you get the value is equal to 2 over 3 of b to the fourth. Okay, so this is 2 times 2, 4, times 2 is 8, divided by 12 is 4 by 8 divided by 12, divide both by 4, so it's 2 over 3. So that's correct. Just double checking my numbers. And then we have the horizontal is equal to the same thing. The width is now 2b times the height is just b, but it's the height that's cubed, and then over 12. And when you add that up, sort out the numbers, you get 1 over 6 b to the fourth. Okay? And so we see that the moment of inertia around the neutral axis for the horizontal one is smaller than for the vertical. The vertical has the highest moment of inertia. And that's where I wanted to make you, so a lot of you, some of you, remember something from the formula that has to do with the distance from the neutral axis. So let's go to the next step. We answered what was required here. Let's go to the next step and answer these questions. I mean, it is obvious to everyone, just when you think about this bending, when you take a bar that's like this, and when you bend it in this position, it's much harder to bend it that way than when it's in this position, okay? And so that's something that should have helped guide you through this problem. But let's look at the next question. What's the absolute maximum bending stress for each? So the bending stress is sigma, right? And that's equal to what? It is equal to a moment times the c and over an I. The c is this distance, right? And the I is one of these two. Okay. And so now let's just write what the c for the both c's, okay? The c for horizontal is equal to what? Just this guy here. That's half the b. And c for this guy, for the vertical, is equal to half of 2b. So that's b. So this one, the horizontal one, is half the size of the vertical c. But let's look at this equation. So yes, somebody said, well, because this is smaller and b over 2 is smaller for the horizontal, and because that fits into here, then sigma will be smaller. Well, yes, but let's just for a moment look at what is important here. The only two quantities here that have to do with the cross section are c and I. We say that we in both cases we loaded with the same moment. So the sigma will be affected by both c and I, with c directly and with I inversely. Okay? So c is what unit? Meters. I is in units of meters cubed. Which of these two you think will have more influence? Okay, I'm glad we agree. It's this guy here, okay? So the moment of inertia has three powers more powers than the C, okay? So that's the one that decides what will be easier to bend and what not, okay? And so we look at the stress. So let's compare the stresses, okay? So I'm writing sigma vertical is equal to, M is the same for both, right? Times C for the vertical is B, and times divided by I for vertical, which is this. So it's 2/3 B to the fourth, and it ends up being the B and this gets canceled, And so it's 3 over 2 m over b to the third. Okay, and now let's look at the horizontal. Is equal to, again, m times, now the c of the horizontal is b over 2, and then the I horizontal is 1/6, b to the fourth, and that comes to be 3 m b to the third. Okay, and so then how do these two compare? It says, how do they compare? Express your answer as a proportion of one with respect to the other. So that means you have to write it, 1 sigma is equal to a number times the other, or 1 sigma over the other sigma is equal to a number. Okay, whichever way you want to write it. Well, let's look at this. This is the same. So this one is 3 over 2, and this is 3. So this guy is half of that one. Of the horizontal. Okay, so that's the sigmas. Okay, now when we're calculating how big how small we can make this part, we're using some sort of maximum allowed stress, right? The absolute maximum bending stress. That doesn't mean we want to maximize the stress. We want that stress to be the smallest. So we want the stress to be the smallest for any part that we have, because we don't want it to go over the allowed stress for that material. Okay? So that means that I really want the vertical, because it's half the stress of the horizontal. So which of the two cases is stiffer? Okay, it's the horizontal one. So I'm going to have to move this up a little in order to solve this. So the vertical is stiffer, and I purposely put this a sign that's not intuitive, because at this point I want you to state the math. It's because this guy is half the horizontal, so the vertical is smaller than horizontal, but I've here put the sign bigger. So all you have to do is say horizontal is bigger than vertical. Okay, that's it. Solved.